Hey everyone, you ready to get technical today? We're diving deep into database system architecture. The core tech that powers basically everything. Online, shopping, streaming, even this podcast.
That's right.
Everything. We're going way past the basics, using this paper, Architecture of a Database System. It's dense, but trust me, this is cool stuff once we unpack it. Think of it like, how a car gets you places? Well, today, we're popping the hood and seeing what makes it tick.
Exactly. We're talking about systems that manage insane amounts of data, keeping it accurate even with thousands of users accessing it at the same time. It's pretty elegant when you get into it.
Right, and the paper starts with this analogy, the life of a query. We're going to follow one request as it goes through the entire system. First stop, it hits the query processor.
This is where the database figures out what you're even asking for, essentially.
So, like air traffic control for data.
Pretty much. Then you've got the storage manager that's all about where the data actually lives. And of course, transaction management, making sure everything happens in the right order.
Okay, so before we get lost in the weeds, let's talk about how these systems are even organized. Because, believe it or not, there are multiple approaches, right? Each with pros and cons.
Yeah, it's kind of like different ways to structure a restaurant kitchen.
Okay, how so?
Well, you could have a bunch of small setups, each one handling all the tasks for a few tables. Or you could have one massive kitchen with specialized chefs for every single dish.
So in database terms, that first model, the smaller setups, that's called the process per DBMS worker model, right?
You got it. And the second one, the specialist chefs, that's your thread per DBMS worker model.
Got it. But this isn't just some abstract choice, is it?
Right.
This has real implications for how well the system performs, how many users it can even handle.
Huge EE implications. Imagine a tiny restaurant suddenly slammed with hundreds of customers.
Total chaos.
Exactly. Choosing the right model is essential for the database to handle real-world use, especially these days with massive amounts of data and users all over.
Makes you realize how important those choices are right from the start.
Absolutely. And the funny thing is, a lot of databases, they were designed before modern operating systems even existed.
Wait, seriously?
Oh, yeah. So they had to get really creative.
So what, they built their own mini operating systems inside the database?
In a way, yeah. Some of them created their own lightweight threads to manage tasks because the operating systems back then just couldn't keep up. Crazy complex, but ingenious.
Let's talk about resourceful.
Right.
But there are databases like DB2 that can actually switch between these models on the fly, right? Isn't that kind of...
Oh, yeah. DB2 is very adaptable that way. It's like having a restaurant kitchen that can totally reconfigure itself depending on what's cooking or how many people you're serving.
That is so cool.
Yeah.
But we're about to get even cooler here because it's time to talk about parallelism.
Now we're getting to the good stuff.
In the simplest terms, it's like having multiple chefs working on different parts of a complex dish at the same time. But in databases, there are two main types of parallelism: shared memory and shared nothing.
Right. So shared memory, that's like all those chefs working in the same kitchen. They're sharing ingredients, equipment, the whole works.
So everyone has access to the same resources. That's got to be efficient, but what happens if someone messes up?
Well, that's the thing. Everyone feels the impact.
Who's in charge of quality control in that situation?
That's what the database has to figure out.
So shared nothing, that must be like each chef having their own separate station, right? Their own tools, ingredients.
You got it. Each chef, or in this case, each processor, has their own resources. And they coordinate with each other over a network, like with headsets or something.
Okay, so it's more resilient if one part fails, but it also sounds like coordination could be a nightmare.
That's the trade-off. Ensuring that the data stays consistent across this distributed system, that's one of the biggest challenges in database design. But we'll get into that more a little later.
Okay, you've got me on the edge of my seat. Now, remember that life of a query analogy from before. Our little query has finally reached the query processor, the brains of the whole operation.
Here's where the SQL magic really happens. Think of the query processor as the head chef who takes your order. They need to understand it, figure out the most efficient way to make it happen, then delegate all the tasks to the team.
So it's a lot more than just grabbing data. There's serious analysis and optimization happening behind the scenes.
Absolutely. The paper breaks it down into 4 main steps. First, you've got parsing and authorization, basically checking for any errors in the query and making sure the user has permission to even access the data.
So like the maitre d', checking your reservation and making sure you're on the list.
Exactly. Next up is query rewrite, where the system tries to simplify the request without changing the end result. It's like the chef finding shortcuts and substitutions that won't impact the flavor of the dish.
Okay, so it's all about efficiency. What's next?
This is where the query optimizer steps in the true mastermind of the operation.
Ooh, I like it.
It looks at all the possible ways to execute that query, factoring in things like indexes, how the data is distributed, even the available resources. The goal, to come up with the absolute best plan, the most efficient path to get the data.
That's some serious strategizing, like a game of chess, but with data instead of pieces.
You could say that.
Yeah.
And one of the most crucial parts of this whole process is selectivity estimation.
What's that now?
It's essentially trying to predict how much data each step of the query will return. You don't want to clog up the works.
So it's not just about finding the shortest route, it's about avoiding the traffic jams too.
Exactly. And this is an ongoing challenge for these systems. As data sets get larger and queries get more complex, the query optimizer has to keep getting smarter and more adaptable to keep up.
Tough job. So we've got our query processor analyzing the request, optimizing the plan, but we haven't even talked about where this data actually lives. Am I picturing a massive warehouse with endless rows of servers? Am I close?
You're on the right track. We're about to head into the world of storage management, where we'll see how databases organize and access those mountains of information they manage. It's more like, imagine a vast, organized library, but for data. That's what storage management is all about, figuring out where to put each piece of information so the database can access it crazy fast when it needs to.
So it's not just about having enough storage space, it's about strategic placement.
Exactly.
Like a library organizes books by subject and author so you don't get lost.
Exactly. And just like a library might have different sections for different types of materials, your rare books, your periodicals, a database can use different storage mechanisms depending on how that data is going to be used. But no matter what, that spatial control, figuring out where things go, that's key.
Okay, organization is clearly vital in the database world. But the paper also mentioned something called temporal control. Are we talking time travel now?
We haven't quite cracked time travel yet, unfortunately, but temporal control is all about managing when that data gets written to the physical disk.
Okay, so less about bending the space-time continuum, more about making sure the data is safe and sound.
It's about finding that balance performance versus data integrity. You want things to run smoothly, but you can't risk losing data, right?
Right. Makes sense.
Yeah.
So how does that actually work?
Okay, so picture a chef who has to constantly run back and forth to the pantry, grabbing one ingredient at a time. Super inefficient, right?
Yeah. That kitchen's not going to get any Michelin stars working like that.
Exactly. Buffering is like giving that chef a tray so they can gather multiple ingredients at once before going back to the stove.
So the database gathers up a bunch of changes and then writes them all together in one go.
You got it. It reduces the load on the disk, makes the whole system run faster. You can't wait too long to write those changes either, otherwise.
Crash. And you risk losing data.
Exactly. It's all about finding that sweet spot.
Balance. We've talked a lot about databases, but the paper also mentions data warehouses.
Yeah.
What are those exactly? Some kind of specialized database.
You could think of a data warehouse as like a massive archive of historical data.
Okay. So if a database is the kitchen, constantly active, a data warehouse is more like the pantry, full of ingredients, but for analysis, for planning.
Perfect analogy. They're not focused on those real-time transactions like, placing an order. Data warehouses are all about understanding trends, patterns, things that happen over time.
Like figuring out what the most popular dish was over the past year.
Exactly. They're used a lot in business intelligence, market research, even scientific discovery. Any area where understanding the history of the data is super important.
But how do data warehouses handle such massive data sets, those complex queries? They must need a special kind of pantry setup.
They do. One thing they often use is specialized indexing techniques, things like bitmap indexes. Remember we talked about B+ trees being like a library catalog?
Yeah, helping you find the exact book or data entry you need super fast.
Right. Well, imagine you're in a library where a lot of books have the same title, but they're different editions. A B+ tree, it would treat each of those as a separate entry, even though they share a ton of information.
Ah, so that's where bitmap indexes come in.
Exactly. They're much more efficient when you're dealing with data that has what's called low cardinality, basically, a limited number of distinct values.
So instead of finding one specific book, it's like finding all the books on a particular subject really quickly.
You got it. And when you're talking about millions, billions of records, that efficiency is crucial.
Makes sense. So it's not just the indexing. Data warehouses also use this thing called bulk loading, right? What is that? Some kind of wholesale delivery for data?
You could say that.
Yeah.
Instead of adding data one record at a time, they load these huge batches all at once,
Yeah.
usually during off-peak hours.
Smart, like restocking the pantry overnight when the restaurant's closed.
Exactly. And because they're dealing with historical data, you don't have to worry about those real-time updates as much. They can use techniques like snapshotting or versioning.
So you can always go back and see what the data looked like at a specific point in time.
Exactly. Powerful stuff. Now, remember how we talked about databases handling more than just numbers and text these days?
Yeah, images, videos, all that.
Data warehouses are the same way. They're evolving to handle all sorts of unconventional data, from social media posts to sensor data. The pantry just keeps getting bigger and more interesting.
But how do they store and process all that different stuff efficiently?
Yeah.
It's like you need a whole new set of kitchen tools.
It requires a special kind of adaptability, something called database extensibility. It's about making the database system open to new kinds of data and new ways of querying it.
So not limited to a fixed menu anymore. The database can handle whatever you throw at it.
Pretty much. One way they achieve this is with what's called abstract data types. So instead of being stuck with just integers or strings, developers can define their own custom data types.
So it's like inventing a whole new ingredient and teaching the database how to use it.
Exactly. That way, the database can understand and process this new data just as efficiently as the traditional stuff. And it's not just about new data types. Database extensibility also lets you integrate with external data sources.
So the database can pull in information that's stored in other systems.
Exactly. It becomes this central hub for accessing and analyzing data from all over the place. Really powerful.
Okay, I am seriously impressed by the flexibility of these systems. But with all this talk about data storage and access, we haven't checked back in with our little query in a while. Where did we leave it on its journey?
Ah, you're right. Our query has successfully navigated the query processor and is about to meet the unsung heroes of the database world, transactions. This is where things get really interesting.
Transactions, the unsung heroes, huh? I'm curious, what makes them so special? We touched on them before, but it feels like we're about to get into some seriously high-level database stuff here.
Think of it like a Michelin star restaurant kitchen.
Okay, I like where this is going.
Timing is everything, right? Transactions are what make sure that each dish, each operation on the data is prepared and served perfectly, even with hundreds of orders flying around.
Okay, now I'm really intrigued. What's the secret to that kind of timing and precision?
Concurrency control. Basically managing multiple things happening at the exact same time.
Right, because with databases, it's not like you've only got one chef working on one dish at a time.
Exactly. So say our little query, it's trying to update a customer's address in the system.
Okay.
But at the same time, another query comes along and it needs to use that same address, maybe for a delivery or something.
Oh, I see the problem.
Yeah.
You could end up sending the package to the wrong place. Or worse, mess up the entire customer record.
Exactly. Total chaos. That's where transactions step in. They're like the expert expediters in that busy kitchen, making sure that orders are processed in the right order, that nothing clashes, and that every dish comes out perfectly.
So it's not just about speed, it's about making sure everything is accurate and consistent.
Exactly. And remember those ACD properties we talked about earlier? Atomicity, consistency, isolation, durability.
Yeah, it's a lot to keep straight.
It's basically the checklist for perfect data management. So atomicity, that means a transaction is all or nothing. If any part of it fails, the whole thing gets rolled back like it never even happened.
No half-baked data in this kitchen.
Exactly. Then you've got consistency. This makes sure that any changes made by a transaction leave the database in a valid state. It's like the chef checking every dish before it leaves the kitchen to make sure it meets their standards.
Quality control. So what about isolation? That sounds kind of lonely.
In a way it is. Isolation means that each transaction is shielded from the others that are happening at the same time. It's like each chef having their own little workspace so they don't accidentally grab ingredients from someone else's station.
No mix-ups.
Right.
And durability, the last one.
Durability, that's the guarantee that once a transaction is committed, those changes are permanent, even if the system crashes. Like imagine the restaurant has a power outage. Durable transactions mean those dishes that are already finished, they're still good to go when the lights come back on.
That's reassuring. But how does the database actually enforce all of this? It can't just be hoping for the best.
All right, definitely not. This is where we get into the mechanics of it all. Remember we talked about locks earlier?
Yeah, briefly.
Locks are essential for isolation. Think of them like place cards on a table showing exactly which data is being used, preventing conflicts.
So locks stop multiple transactions from trying to modify the same data at the same time.
Exactly. And there are different types of locks, too. You've got shared locks, which let multiple transactions read the same data at the same time. Think of it like everyone at the table sharing a menu.
Makes sense.
Then you've got exclusive locks, which give one transaction the sole rights to modify some data, like a chef claiming a specific ingredient for their dish.
Okay, so shared locks are for reading, exclusive locks for writing. What happens if one transaction wants to modify some data that another transaction is just reading? Does everything grind to a halt?
Not necessarily. Databases use some pretty smart algorithms to handle those situations. One common approach is lock waiting. The transaction that needs the exclusive lock, it just waits patiently for any shared locks to be released.
So it's like a line of people waiting politely for a table to open up at a busy restaurant. But what if a transaction gets stuck waiting for a really long time? Doesn't that slow the whole system down?
That's a good point, and it's a real concern. That's why databases have strategies to minimize something called lock contention. Basically, they try to be smart about which locks they acquire, when to release them, that kind of thing.
It's like having a good maitrette who knows how to manage the reservations and the seating chart so that everyone gets seated and served quickly.
Exactly. Now, there's one more piece of the puzzle we need to talk about. Logging. Do you remember us mentioning that earlier?
Vaguely. It's related to durability, right?
Yeah. Right. Think of logging like having someone meticulously writing down every single action that happens in the kitchen, every ingredient chopped, every sauce stirred, every dish plated. It's all recorded in the log.
Okay, so it's like a detailed recipe book, but instead of ingredients, it's tracking data changes.
You got it. And this log is crucial if the system crashes, because then the database can use it to retrace its steps to recover to the last known good state. It's like having a backup recipe so you can recreate the dish even if there's a minor cooking mishap.
That's incredibly clever, but doesn't all that writing slow the system down?
It's a valid concern, but databases are designed to handle logging really efficiently. One common technique is something called write-ahead logging. Basically, they write the changes to the log before they even apply those changes to the actual data.
So it's like writing down the recipe steps before you even start cooking. That way, even if you get interrupted, you can always pick up where you left off.
Exactly. That way, even if there's a sudden crash, the database can use that log to recover any transactions that were committed and ensure that the data is consistent.
Wow, this whole system of transactions, ACD properties, logging, it's incredibly intricate, but so well thought out. It's like this perfectly choreographed dance happening behind the scenes, making sure the data always stays accurate and reliable.
It really is a testament to how much work has gone into designing these systems, constantly refining them to handle the demands of, well, pretty much the entire internet.
It's amazing. You've definitely given me a whole new appreciation for what's happening behind the scenes every time I use a database. It's like this hidden world of complexity that we never really see.
And it's a world that's constantly changing and evolving, especially with cloud computing, big data, all of that.
Sounds like an exciting field to be in. Well, you've been listening to the Deep Dives, where we take complex topics and make them accessible. Today, we took a deep dive into the inner workings of database system architecture. We highly recommend checking out the full research paper, Architecture of a Database System, if you want to learn even more. And as always, stay curious and join us next time for another deep dive.